The last thing we need to talk about before we start working practice problems is carbon-13 NMR. So carbon-13 is done similarly to hydrogen NMR. We are still using the same instrument, but the difference here is the abundance of carbon-13. So carbon-13 only makes up 1% of carbon, so we are not going to get the information as we would with hydrogen NMR, because with 1% there is not enough of carbon-13 to get information about all the details. So we don't get multiplicity or integration information with carbon-13. But what carbon-13 tells us is how many different carbons there are with different environments. So if you look at this spectrum, this is the carbon-13 spectrum. We have 1, 2, 3, 4 signals, meaning that we have 4 different carbons in our molecule. So we still look at the environment. Every type of carbon that is in the different environment, it's going to show up as a separate signal, and that's the most important information that we are going to get from carbon-13 NMR. So another information that we can get from carbon-13 is about chemical shifts. So this can give us some information about the environment again. So we see carbons that are attached to more electronegative atoms appear at higher ppm, so somewhere right here. So the scale is very different in carbon-13. Here we go from 0 to 200 ppm. In proton NMR we go from 0 to 12, but we still get almost similar information. So if we see a carbon is further downfield, we can expect that it's connected to oxygen, bromine, nitrogen, or any other electronegative atom. So as I mentioned, we don't have any integration in carbon NMR. We cannot report integration in carbon NMR. But generally we can say quaternary carbon, which is a carbon that is connected to 4 atoms other than hydrogen, usually show a weaker signal in carbon NMR. So if you look at this structure, the only carbon atom that is connected to 4 atoms other than hydrogen is the carbon of carbonyl, and here is the signal for that. So if you look at the intensity of this signal, it is actually very weak signal. So if you look at the height, it's not very strong comparing to the signals that belong to carbons that are connected to hydrogen atoms. So this is actually a good sign. Whenever you see a signal, a very weak signal in carbon NMR, you can think about possibility of presence of quaternary carbon in your molecule. So once again, based on this carbon NMR, we expect to have at least 4 carbons in the structure of the compound. But don't forget that we could have symmetry. So if the compound is symmetrical, we might have more than 4 carbons in the molecule, but 2 of them show up at the same place in carbon NMR, so we see less signals in carbon NMR. Now, how do we know that? You should always look at the molecular formula. So if in the molecular formula you have a specific number of carbons, and in the carbon NMR you see less signals than the number of carbons, you should always think about symmetry in the molecule. Now, once again, you will not see multiplicity or integration in carbon NMR, so you don't see doublet, triplet, quartet. Every single signal means that you have a different carbon. So for example, if you see 2 signals right beside each other, for example these 2 signals, or even they are closer to one another, you shouldn't think about having a doublet in the carbon NMR. Okay, we cannot have multiplicity. These 2 signals means that we have 2 different carbons in carbon NMR. Now, how can the symmetry influence the number of signals in carbon NMR? So we can see symmetry in the same way that we saw in proton NMR. Now we are looking at carbons. So if you look at the first structure, we have a plane of symmetry that passes through the molecule right here. Now this plane of symmetry makes these 2 methyls to be exact the same. So we are going to see 1 signal for them. This carbon is the same as this carbon. Both of them are connected to methyl, so they have the same chemical environment. This carbon is also exactly the same as this one. So they are 2 carbons away from the methyl group, both of them. So we are going to see same signal for them. And these carbons at the bottom, they are also the same. So overall, we are going to see 1, 2, 3, 4 signals for this molecule. Now, as I mentioned, symmetry can influence the number of signals in carbon NMR. So basically, if the molecule has the symmetry, the number of signals in carbon NMR is going to reduce. So meaning that we have 4 signals in carbon NMR, however, this molecule has 8 carbons. So whenever the number of signals is lower than the number of carbon in the molecular formula, you should always think about symmetry in the molecule. Now with the second structure, we have plane of symmetry that passes through the molecule right here. So that makes this methyl to be exactly the same as this one. This carbon is the exact the same, so we are going to see 1 signal for them. This carbon is also exactly the same as this one, and we count the atoms that are on a plane of symmetry. So we are going to see 1, 2, 3, 4, 5 signals for this molecule. And with the third one, we have 2 plane of symmetries. So with this plane of symmetry, this carbon is exactly the same as this one. This carbon is exactly the same as this one. The methyl is exactly the same as this one. Now with this plane of symmetry, this carbon is exactly the same as this one, and this one is exactly the same as this one. So overall, we are going to see 3 signals for this structure. Now let's look at this example and decide how many signals you can see in carbon NMR for this structure. So the first step is to decide whether we have symmetry here or not. Yes, we do have a symmetry here. So we have 1 plane of symmetry right here, and we have another plane of symmetry right here. So with this plane of symmetry, this carbon is exactly the same as this one. So we are going to see 1 signal for both of them. So that gives us 1 signal. Again, with the same plane of symmetry, this carbon is exactly the same as this one. So we are going to see 1 signal for both of them. Now with this plane of symmetry, this carbon is exactly the same as this one, and this one is exactly the same as this one. So overall, we are going to see 2 signals for this structure. So another practice problem, we want to know how many signals we can see in carbon NMR for this structure. So we are still looking at carbons, and we are looking at different environments. Now, do we have plane of symmetry in this molecule? Yes, we do. So we have a plane of symmetry that passes through the molecule from here. Okay. Now with this plane of symmetry, we can see a signal for the carbon of carbonyl. Then this carbon would be exactly the same as this one. Both of them are connected to carbonyl, right? So we are going to see 1 signal for both of them. This carbon is exactly the same as this one. So we are going to see 1 signal for both of them as well. Now looking at these 2 methyls, what happens to our methyl groups here? So if you remember previously, we said that methyl groups that are connected to the same carbon should be the same. And that is true when we have a single bond. With the single bond, we can have a free rotation about this bond, so these 2 methyl groups will be identical. However, right now, we have a double bond, and we know that we don't have rotation about the double bond. So these 2 methyl groups should be different from one another. However, this plane of symmetry makes this methyl to be exactly the same as this one. Both of them are closer to the carbonyl group. Basically, we say that they are cis to the carbonyl group. However, this methyl group is exact the same as this one, and this is different from this methyl group. This methyl group is trans to the carbonyl. It is far from the carbonyl group. Therefore, we are going to see one signal for this methyl group and this one, and another signal for this methyl group and this one. So overall, we are going to see 5 signals for this structure. Now let's make a note of that. So why are 2 methyl groups connected to double bond are not equivalent? Because we don't have free rotation about the double bond, and that makes the top methyl group to be cis to the carbonyl group. And basically the bottom methyl is trans to the carbonyl group. So basically they don't have exact the same chemical environment, they have different environments, so we are going to see 2 different signals for both of these methyl groups. And that is true when we have double bond. With the single bond, these 2 methyls should be exact the same because we have free rotation about the single bond. But with double bond, we don't have free rotation, so they are different. So like hydrogen NMR, chemical shift for carbon NMR is also affected by presence of electronegative atoms. So most of the time with alkane, we see 0 to 50 ppm. If the carbon is connected to an electronegative atom such as oxygen, nitrogen, chlorine, bromine, we usually see them between 50 to 100, and in the same region we see sp hybridized carbon as well. So carbon-carbon triple bond appears in this region. Carbon-carbon double bond or sp2 hybridized carbon appears between 100 to 150. And carbonyl CO double bond, we usually expect to see that somewhere between 150 to 220 ppm.